Thanks for the intro. And hi, everyone. The authors of this paper cannot be here due to the visa issues. I'm Fuchen Ma from Tsinghua University, a postdoc researcher from the same lab as the authors. And it's my pleasure here to introduce this work named DDLumos to you. And first, I'll briefly introduce the atomic DDL and the bugs it can cause. Atomic DDL requires that data definition statements such as create, alter, and drop either succeed in their entirety or roll back completely, ensuring the database is never left in an inconsistent intermediate state. And this concept emerged because traditional non-atomic DDL operations can severely undermine the data consistency and availability. And here we give an example. Consider an issue that exists in MySQL versions prior to version 8. And first, it executes operation like create table T1. And this operation creates a table. And second, it executes a drop table T1, T2. And here we can see that the table T2 does not exist. So the entire statement false. And here is the critical question occurs. Was the table T1 deleted or not? And under non-atomic DDL semantics, T1 may already have been dropped, producing an unpredictable result and breaking consistency guarantees. To mitigate this problem, database vendors introduced the atomic DDL. And the key idea is to bundle data dictionary updates, storage, engine operations, and binary log writes into a single all or nothing transaction. And there are two implementation strategies are commonly used today. And the first is native atomic DDL support. And the engine itself guarantees that each DDL statement is atomic. For example, MySQL version 8 adopts this strategy. And the second one is to allow the DDL statements to be executed inside a transaction. However, the implementation of atomic DDL is complex due to the involvement of multiple components. And all of these components must work together to ensure the atomicity and the consistency during the schema changes. And as a result, implementation errors in this mechanism are difficult to avoid. We define these errors as the atomic DDL bugs, or short as ADBs. And here we present an example of atomic DDL bugs in MySQL, which is caused by the implementation errors in the rollback mechanism. And here we have an operation like the alter table statement. And it tries to drop a column C1 and add a new column C3 in table 1. However, it falls due to the foreign key constraint. Therefore, table T1 would still have one column C1. But the alter table statement is not correctly rolled back, resulting in the T1 table having two columns. Here is the C1 and C3, which is inconsistent with the expected state. And DBMS underpin countless critical applications. So an atomic DDL bug can lead to severe economic losses and even more serious consequences. But the existing testing tools are unable to expose such bugs. Classic DBMS fuzzers and query generators focus on producing syntactically valid cycle, but they provide no dedicated mechanisms for crafting inputs that trigger atomic DDL bugs. And moreover, we still lack a systematic understanding of how these DDL bugs manifest and propagate, and leaving us without clear test oracles for detecting such bugs. To answer these questions, we first conducted a comprehensive study. And we collected 207 real-world atomic DDL bugs reports from 3 popular DBMSs, including MySQL, MariaDB, and PostgreSQL. And these bugs are collected from their bug checkers with specific search keywords. And our methodology involved the deep analysis of these reports, including their characteristics and root causes. And here we have some general findings from the study. First, for the manifestations of the atomic DDL bugs, among the studied bugs, we find that about 44% of them manifest as incorrect result, and about 32% manifest as post-recovery data inconsistency, and about 24% of them manifest as system unavailability. And for the second finding, for the root causes of atomic DDL bugs, we manually checked each bug report and further identified several underlying causes that directly contribute to the manifestations described earlier. We discovered that all the ADBs are caused by the implementation errors of atomic DDL. And specifically, 4 main causes of ADBs are identified with the following distribution. The first part is incomplete rollback mechanisms, accounted for 32%, and improper synchronization for 22%. Implemented errors in the concurrency control for like 18%, and the incorrect error handling for the last 22%. And here is the third finding. For the triggering conditions of the ADBs, we analyzed the relation of DDL statements in the cases and find that about 93% of the ADBs are triggered in scenarios involving data conflicts between DDL statements. And in that statements, multiple DDL operate or interact with the same metadata elements in the test case. Here we give an example of metadata conflict points. We define the metadata conflict points as the specific locations in the test case where multiple DDL statements operate or interact with the same metadata elements, such as a table, a column, an index, or constraint. And these conflict points reflect the data dependency between different statements, which can help trigger more code behaviors of atomic DDL for detecting ADBs. And in addition, we also analyzed the trigger scenarios and summarize the 3 test oracles. For the first one, the test oracle is named as incorrect results, and they are identified by comparing the execution output and the metadata. And the second oracle is named the system unavailability, and this is detected by checking the server's response after executing the test cases. And the last one is named the post-recovery data inconsistency. It occurs when the server is restarted mid-atomic DDL execution. And if the recovery metadata differs from the expected state after the rollback, developers confirm it as a bug. And based on the analysis, we designed the DDLumos to detect atomic DDL bugs. And here is the overall design of the tool. And it includes 2 main components. The first is test case generator for generating test cases with metadata conflict guided DDL synthesis. And the second one is a metadata consistency analyzer for detecting atomic DDL bugs with graph-based consistency analysis. And the process follows 4 main steps. In the first step, DDLumos initialize a metadata table to record schema elements used during the test case generation, as well as the metadata conflict points associated with each DDL operation. And in the second step, DDLumos alternates between generating DDL statements and other cycle statements. After each DDL operation, DDLumos analyzes the resulting metadata conflict points and updates the metadata table accordingly, guiding subsequent DDL generation to maximize the conflict scenarios. And in the third step, DDLumos constructs a metadata graph for the generated test cases and sends them to the target DBMSs. And the metadata graph captures the relationships between schema elements before and after DDLs, providing a structural foundation for analyzing schema consistency and correctness. And in the fourth step, DDLumos uses the metadata graph to detect ADBs by comparing the execution results with the predefined detection scenarios for 3 bug manifestations. And then we detail the core method of each component the metadata conflict guided DDL synthesis and graph-based consistency analysis. And in the DDL synthesis part, the approach consists of two steps. It named conflict point checking and the test case synthesis, which work together to trigger deep behaviors of atomic DDL. And based on the force finding, incorporating metadata conflict points into DDL test cases significantly increases the likelihood of exposing ADBs. And to achieve this, DDLumos continuously collects and updates metadata information during test case generation, using these details to get the synthesis of subsequent DDL operations. And the left figure shows an example of the metadata information collection to checking the conflict points. And then DDLumos checks the conflict points in its metadata table and crafts mixed DDL sequences that trigger those conflicts to expose atomic DDL bugs. And for each statement, it chooses the type, sketches the structure, and fills in objects from the metadata, iterating until the test case is complete following the red algorithm. And after generating test cases using the metadata conflict guided DDL synthesis part, DDLumos distributes the test cases across multiple client threads while controlling concurrency based on the sequence of these statements. Besides, DDLumos employs graph-based consistency analysis to verify the correctness of test case execution results. And this analysis involves two critical steps. And the first step, for a test case, DDLumos constructs a metadata graph that represents the schema elements and their relationships before and after executing each DDL statement. And then, based on the metadata graph and DDL execution scenario, DDLumos analyzes the metadata state resulting from the DDL operations. It compares the expected metadata derived from the graph with the actual metadata in the database after the statement execution. And any disconsistency between the expected and actual metadata indicate a potential atomic DDL bug. And here is our evaluation result. We use DDLumos to test 6 DBMSs, including PostgreSQL, MySQL, MariaDB, and others. DDLumos successfully discovered 73 bugs, including 20 system unavailability bugs, 31 incorrect result bugs, and 22 post-recovery data inconsistency bugs. And all of these bugs have been confirmed, and 14 of them have been fixed by the corresponding vendors. And here are two examples of the bug to show how we detect the atomic DDL bugs. And the left one is a case of incorrect result in MySQL caused by the implementation errors in metadata synchronization. And the right one is a post-recovery inconsistency case in GridSQL caused by the errors in rollback mechanisms. And we also compare DDLumos with state-of-the-art tools like CycleLancer, CycleSmith, Scoro, and TXCheck. And we conducted a 48 hours experiment, and the results show that the test cases of DDLumos have metadata conflict points, and DDLumos finally cover more related branches than others. In addition, we also calculate the number of detected bugs. The result shows that DDLumos find more unique bugs than other tools. And among the unique identified 36 bugs, most of them are not covered by other tools. So to summarize, in this work, we analyzed 207 atomic DDL bugs to understand their characteristics and root causes. And based on the study findings, we designed DDLumos and detect atomic DDL bugs consisting of metadata conflict-guided DDL synthesis and graph-based consistency analysis. And we implemented DDLumos and find 73 real-world bugs in 6 popular DBMSs. And that's all. And if you have any question, please send an email to ask the authors. Thank you.